let's try this again. Okay, RL circuit or LR circuit, same thing. Here we still have a battery. It still has an EMF. We still have a switch. We still have a resistor. And we still have an inductor. And we still want to analyze it mathematically. But we're not going to use Kirchhoff's loop rule because it's an approximation. What we want to use is something that is a property of the universe that is not an approximation. So that something is Faraday's law. Faraday's law tells us, has that same term in it. The integral of E dot dl equals minus d phi b dt. Right? This is the EMF generated in Faraday's law, and this is the rate of change of the magnetic flux through a loop. So for Faraday's law, we've got to define this loop. Right? So what we say is the loop for the circuit is the loop that goes down the middle of this wire. Right? The switch is closed, go through the wire, we go through the resistor, right? And we go through the wire that makes up this coil. So literally the circuit is the loop, like that. If I were going to, I could give it hatch marks like that. Right? There's our loop. And when you look at it, you might say, are we including the B field or not in this loop? It's a little bit, maybe we are. Well, it's very hard to visualize, but if you take a coil and you define it as part of a loop and think about what was really making the inside of the coil, or what's really making the surface that you're defining, it actually does go and include, in a way that I'm not going to draw very well, the part inside the coil. So my point is, the magnetic field created inside the coil will penetrate this loop. Okay? If you work it out, or if you get a coil and dip it in a soap film and pull it up, you get this weird spiral shape, and the field does penetrate the spiral shape. So we are including in our circle the d phi b dt that's inside the inductor. It's in there. Okay? Okay, so we want to do Faraday's law, and we don't want to think about Kirchhoff's loop rule, but I will allow us to think about the potential differences a little bit. So all I'm going to do is put the negative sign over here, right? Minus the integral around the loop of E dot dl, and then get rid of that minus sign is d phi b dt, right? Faraday's law. Okay. And now you can see this is the definition of the potential difference. So I did this so we can say, okay, if we go around the loop and we go across the battery, what do we get? Well, just like in Kirchhoff analysis, we get the EMF. Right? The electric field in the battery, if this is positive and negative, points down, and we're walking against it, so that's negative. E dot dl is negative, but then this comes out negative. We get the EMF. Right? And we're walking through the wire, walking through the wire, walking through the wire. Nothing happens here. There's no field. Potential's constant. And then here, with a resistor, you get an electric field in the resistor pointing that way, right? And the current, we're assuming, is going that way. So that's minus IR. So similar term to Kirchhoff analysis. You get minus IR because you actually do get an electric field in a resistor. Think back to our Drude model discussion. And then you go through these highly conductive wires, and there's no resistance in this wire. So you don't really get a term from there. Right? There's no field inside that wire. See, that's all you have for E dot dl. Okay? But now, according to Faraday, the right side is not zero. We're creating a back EMF. We're creating a non-conservative field that's equal to d phi b dt. And you know from our discussion of inductors, d phi b dt is the same as L di dt. Right? Calling it the inductance L is just our way of not having to calculate the exact magnetic field in the geometry every time. Right? We know that the current and the magnetic field are proportional, so we just call it L di dt. So this is the proper equation. Okay? This, you could say, is like Kirchhoff's delta V's. And if you do, I will yell at you, because it's not Kirchhoff's delta V's. This is Faraday's E dot dLs. Right? And this is Faraday's d phi b dt. This is Faraday's flux. And you can see why it's tempting to use Kirchhoff's analysis, because all we do is bring this over here, and we get the EMF minus I times R minus L di dt equals 0. This is our differential equation that we would use to solve for the current as a function of time. And you can see it looks just like what we got with Kirchhoff's loop rule. EMF minus IR minus L di dt equals 0. Problem is, this one is for the wrong reason. And this one is for the right reason. It's because of Faraday's law. So, surprisingly, most books really either they choose not to discuss this or they don't understand it. I don't know. A lot of books will have a teeny little caveat that doesn't make a lot of sense when they present it, when they literally say the potential drop for Kirchhoff's loop rule for the inductor is minus L di dt. So the book I usually use says Kirchhoff's rules were developed for circuits with steady currents, but they can also be applied to a circuit in which the current is changing if we imagine them to represent the circuit at one instant in time. No, they can't. Okay, so if the current is at one instant in time, it's not changing and you lose your whole inductive effect. So really, there's really no justification. I've read another book that says, well, you can do it as long as you imagine that the current is changing very slowly. Well, if the current's changing very slowly, then there's really no back EMF. Right? You're taking the limit where this doesn't happen at all. So what's interesting is usually when something gives you the right answer for kind of the wrong reason, it's usually because you've made an approximation. That would be the case where it's where the current is changing slowly. This isn't really an approximation. This is just wrong. It just happens to come out right, but not really for a good reason. Right? This is really what you should do. Now, I don't want to get in trouble with the physics community, so in the rest of the videos, I'm just going to say I applied Kirchhoff's loop rule. Okay? So this is the only video where we're going to talk about this. Right? Everything else, it's just Kirchhoff's loop rule. It'll match your book. Everybody will be happy.